Okay, so our agenda for this review is we'll cover the chain rule briefly, then we'll talk about implicit differentiation, related rates, finding extrema, and then lastly Rolle's value and the mean value theorem. So let's go ahead and get started with the chain rule. And the chain rule is basically just a way of taking derivatives of more complicated functions. And if we wanted to write it out formally, we took the derivative of some function of u. It's going to be where u is a function of x. And basically all that means is if we have some more complicated function, for example, sine of 3x, we just take the derivative of the outer part first. So the derivative of sine is cosine. We leave the inside the same, and then we multiply by the derivative of this inside part right here. So the derivative of 3x is 3. And if we wanted to look at a more complicated example, for example, cosine of sine of x plus 1 cubed, well, all we do is we start looking at the outside. The derivative of cosine is going to be negative sine, and we leave the inside the same, so sine of x plus 1 cubed, then times the derivative of the inside. So then, in order to take the derivative of the inside, we're actually going to need to use the chain rule again. So first, this is going to be our new outer function, the sine of x. So the derivative of sine is cosine. Leave the inside the same, x plus 1 cubed times, now we have to take the derivative of this inside part again. And then the derivative of x plus 1 cubed is going to be 3 times x plus 1 squared. Lastly, times the derivative of this inside part of x plus 1 cubed, which is just the derivative of x plus 1, which is 1. So if we just knock that off, just times 1, it doesn't do anything. This should be our whole derivative. That's what happens if you have the chain rule several times in a row. So we're actually going to do a couple of practice problems really quick. Go ahead and try out cosine of x sine x. Go ahead and take the derivative of that. And then also sine squared x squared. see. For number 1, let's actually work through it and see what we get. So by applying the chain rule, first we take the derivative of cosine x. So minus sine, we leave the inside alone. X sine x. Then we take the derivative of the inside. And since this is two functions multiplied together, that's going to be the product rule. So we take the derivative of the x first, we get sine x. And then we take the derivative of sine x, we get plus x cosine of x. In this case, it might simplify to something. Let's see. But it looks like you didn't quite use the product rule on the inside, which is unfortunate. I mean, it's just a tricky thing to remember. Sometimes you have to compound the chain rule with the product rule. It is important to notice that I think that the trick here is mostly to recognize that this inside part, once you take the derivative of it, it's like a whole new function. So you can think, what's the derivative of x sine x? And then you can say, well, that's going to be using the product rule, sine x plus x cosine x. And then you can just take this whole part, plug it in right here. Make sense? Cool. The second one, I think I'll just go ahead and, do you want to work this one out, or would you like me to just work through it? All right, I'll just work through it then. First off, I'm going to rewrite it just to make things a little clearer. We can think of sine squared x squared as sine x squared, and then all of this squared. So that makes it easy to see that our outermost thing is clearly going to be this squared part. So using the power rule, we can say that's 2 times sine of x squared, then multiplied by the derivative of the inside part. And in this case, the derivative of the inside part, our inside part is going to be this sine of x squared. So the derivative of sine x squared is going to be cosine of x squared. And now our new inside part becomes this x squared portion. So then we multiply by 2x. And that gives us 4x sine of x squared cosine of x squared. And we could simplify that further using trig identities, but for now, this is all I'm going to do. Make sense? All right. In that case, we're going to move on to implicit differentiation. And first, we'll talk about the difference between an explicit function and an implicit function. An explicit function is a function that's written in the form of y equals or x equals, or in other words, one of the variables is written so that that variable is by itself on one side, and on the opposite side is a function of completely different variables. So for instance, y equals x squared plus 3x is an explicit function, but y equals x squared plus 3x plus y squared is not an explicit function because you have this y squared on this side. And if a function is not explicit, we call it implicit. And you'll see this form a lot where you have like 2x plus 3y equals to some constant, so like 2 or something like that. Basically, all of your variables are on one side and just a constant is on the other, but you can really see implicit form as anything that's not explicit. So for instance, 2x squared plus y squared equals y cubed minus x. That's also an implicit form. But then the question is, how do we take the derivative of these implicit form functions? Because we can't necessarily just have it's not all in terms of one variable, so it's a little confusing. And that's where implicit differentiation comes in. And the trick with implicit differentiation is when you're taking the derivative, x's goes to 1, and y's become dy's over dx's. And you treat each variable as its own function. So for instance, if you have x times y, you would have to use the product rule on this. And let's actually go ahead and do an example just because that makes things a lot more clear. For instance, if we had x squared plus y squared equals to 9, then in order to take the derivative, we just treat every variable like its function. So the derivative of x squared is 2x, the derivative of y squared is 2y, but then our y's become dy dx's. So multiplied by dy dx, and then the derivative of 9 is just 0. And then in order to get our derivative is in form of dy over dx equals to something. So to isolate dy dx in this situation, we subtract 2x over, and then divide by 2y, which gives us minus x over y. And this is a pretty simple example. So let's go ahead and do one that's a little more complicated. For instance, x cubed y cubed minus y is equal to x. In this case, we just start by taking the derivative. We've got an x cubed times y cubed, so we're going to need to use the product rule. We get 3x squared y cubed plus x cubed times 3y squared dy over dx minus dy over dx equals to 1. And the trick to isolating your dy over dx is to just put everything with the dy dx on one side and everything without it on the other side. So we get x cubed, 3x cubed y squared dy over dx minus dy over dx equals to 1 minus 3x squared y cubed, just by subtracting this 3x squared y cubed over. Now, since everything on this left-hand side has a dy over dx, you can just factor that out like this. And then we just divide everything by whatever's on this side that is not dy over dx. So in this case, it's 3x cubed y squared minus 1. And we do that to both sides. So then we end up with dy over dx is equal to 1 minus 3x squared y cubed by 3x cubed y squared minus 1. So not too difficult. One side note, earlier I said that your x's become 1 and your y's become dy over dx. There is another way you might see it, where your x's turn into dx's and your y's turn into dy's. This is less common, but it can be useful at times. So for instance, if you have, let's say, we'll just go over the first example briefly. Again, if I can actually, I'll just take a space. Okay. So if we wanted to go over the first example again, we would have x squared plus y squared equals to 9. In this case, if we were using dx and dy's, it would become 2x dx plus 2y dy equals to 0. And then really your second step after taking the derivative is just to divide everything by dx. So in this case, it would become essentially, I'm actually going to split this up just for sake of clarity. You can see it would be like if dx is canceling. This isn't what's happening like technically mathematically, but it's just a good way of visually seeing what happens. That should be a plus sign. And this is actually the same step we were at earlier, and we end up with the same result, that dy over dx is equal to minus x over y. So this is just an alternate way you might see it, implicit differentiation done. So just watch out for that. Regardless, let's go ahead and do a couple of examples, or practice problems, sorry. Let's start with 2x cubed plus 3y cubed is equal to 64. And also, as our second example, find the second derivative of x squared plus y squared equals to 1. How's it coming? equals. All right. Let's work it out and see. I have not actually worked this one out yet. So we'll go ahead and start. Our 2x cubed becomes 6x squared. Our 3y cubed becomes 6y. Sorry, that should be a 9y. 9y squared dy over dx. So then 9y squared dy over dx becomes negative 6x squared. So then dy over dx is minus 6x squared or 9y squared, which is correct. That's what you got. If we wanted to simplify it, we could just a bit. Go to minus 2x squared over 3y squared. All right. And number C. I think number 2 is negative 2x over 2y. All right. Let's go ahead and work it out and see what we get. So first off, we need to find our first derivative, dy over dx. So you get 2x plus 2y dy over dx equals to 0. So then 2y dy dx is equal to negative 2x. So dy over dx is equal to negative x divided by y. So then if we wanted to find our second derivative, we need to take the derivative of our first derivative. And we get d squared y over dx squared is equal to, in this case we'll have to use the quotient rule. That's going to be the low that's on the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Just like that. And if we simplify for some signs, we get that that's a negative dy over dx, so that's a positive dy over dx minus y from up here, this coefficient. It's front y all over y squared. But then we already know that dy over dx is equal to minus x over y. So we can actually plug that in for our dy over dx in our equation that we found. So then d squared y over dx squared is equal to minus x over y minus y all over y squared. Of course, we don't want to leave a fraction within a fraction, so we can just multiply all of this by y divided by y. So that's negative x minus y squared over y cubed. Because we're finding the second derivative. If that makes any sense at all. Does that make sense to you? All right, glad to hear it. And I'll just write dx squared, just so anyone watching this later can see the answer. Okay, moving on from implicit differentiation, we get to something called related rates, which actually uses implicit differentiation to solve actual real-world problems as far as you can in perfect mathematics. Okay, I'm just writing implicit differentiation again. It's not bad. And the thing behind related rates is, let's say you have a function relating two different quantities. So radius and volume. For instance, you got a function v equals to 4/3 pi r cubed. This is given for volume of a sphere, given the radius. And you know that, let's say you have a sphere and it's a balloon, and you're pumping in air at 100 centimeters a second. Then we can say that our change in volume with respect to time is 100 centimeters squared per second. But let's say you want to know how fast the radius of the balloon is changing when r is equal to 8 centimeters. Then actually we're going to do all of this in meters. This is going to be a huge balloon. It's like a very large weather balloon. The equation relating these two quantities, you've got a change in volume with respect to time, and you know a radius. Then we can actually, if volume and radius are related through a third variable, time, then we can actually take the derivative of this equation we have with respect to time, and that'll give us an equation relating the rates of change of our two variables, volume and radius. So if we take the derivative implicitly with respect to t, you'd get dv dt equals 4/3 pi is a constant, so the derivative of r cubed is 3r squared. Then multiply by dr dt, because this is also treated as a variable that we need to take the derivative of implicitly. We simplify that, our 3's cancel, so we get 4 pi r squared dr dt. And in this equation, in this problem, we're actually looking for dr over dt. That is the rate of change of the radius when the radius is 8 meters. So now that we've actually got this equation, d over dt equals to 4 pi r squared dr over dt. You can actually see we have two of our unknowns. We know dv over dt and we know our r. So this is just an equation with one unknown. We can just plug in everything that we know. So 100 equals 4 pi times 8 squared times dr over dt. And that leaves dr over dt to be equal to 25 divided by 64 pi meters per second. Does that make sense? Great. I'm actually going to do a second example because this is a problem that tends to confuse a lot of people. And it's a problem that involves angles. So let's say that a boy loses his balloon. It is sad, but oh well, we needed it for the math problem. So his balloon is floating upwards at 5 feet per second. So an observer 50 feet away looks at the balloon and he notices it's pi over 6 radians above the horizon because he is in a math problem, so he notices things like this. And the pi over 6 radians is going to be equal to our angle theta. With related rates problems, it's often helpful to draw a picture. So we're going to draw a picture right here. We have a triangle, we have our angle theta. This is our height h. We know that this distance is 50. Here's the balloon up here. Here's the observer. And this is where the little boy was. This is the little boy right there. So now we have our whole picture and all of the information that's been given, and we want to know what is the rate of change of the angle when the angle is pi over 6. So first, what we need to do is we need to identify what we're looking for. In this case, it was given. We're looking for the change of theta with respect to t. We also need to write an equation relating what we're given to what we have. So in this case, we have dh over dt, and we have theta. So we want to write an equation relating h and theta, and we can do that using trig. So in this case, we have our adjacent and our opposite sides, sorry. So that tells us we're going to be needing tangent. We know that the tangent of theta is equal to opposite over adjacent. Or in other words, 50 tangent theta is equal to h. So here's our equation. Our next step is going to be to take the derivative of this equation. The derivative of tangent is secant squared, but then by the chain rule, we need to multiply by the derivative of the inside, and the derivative of theta is d theta over dt. And then that is equal to the derivative of h, which is dh over dt. And again, you'll notice that here we've got an equation with 3 unknowns, but we actually know 2 of them, so we solve for our unknown that we're looking for, d theta over dt. So 50 times secant squared pi over 6 equals times d theta over dt, is equal to 5 feet per second. So then this becomes d theta over dt is equivalent to 5 over 50 secant squared pi over 6, which is equal to 1 over 10 tenth times 1 over cosine, 1 over secant is cosine, so that's cosine squared pi over 6. Like that. And then cosine of pi over 6 is equal to the square root of 3 over 2. So that's the square root of 3 over 2 squared, which is equal to 1/10 times 3/4. So d theta over dt is equal to 3 over 40 radians per second. One thing to note with these angle problems is you almost always want to use radians when you're solving them, because otherwise you end up with your conversion things. Basically, you don't want your angle to have units of degrees, because otherwise it'll throw off your answer. So that's just one thing to be careful of. But other than that, that's the whole process. Steps involved are, first you need to identify what you're looking for. So in this case, we said we need to find d theta over dt. Then you need to think and write an equation relating what you're looking for. In this case, it was d theta over dt with what you're given, which is dh over dt. And in this case, we wrote our equation relating theta and h, because we knew that when we took the derivative, that would result in a d theta and a dh. So then after you write this equation, you take the derivative, and then you simply plug in what you're given and solve. So why don't you go ahead and try a sample problem. And that is going to be, you have sand in a pile, and it is being added at a rate of 2 meters cubed per second. And you also know that the height of the pile is equal to the radius. And we want to know how fast does the radius change when the radius is equal to 5 meters. And just so you have it, this is the volume of a cone with radius r and height h. So go ahead and try that one out. And times pi over 3 over 2 meters per second. Let's see. I'm not quite sure that's what I got. Let's work through it. So our first step is we need to figure out what we're looking for. We're looking for dr over dt, change in radius with respect to time, when our radius is equal to 5. So the first thing I notice is h isn't necessarily a concern because we don't have a dh and we're not looking for a dh. So we need to get this h out of our equation. We do that using this h is equal to r. So if we just make a substitution, we just replace our h with r. So then our equation that we actually want to take derivative of is v equals to pi over 3 times u. Make sense? Is that what you did? All right, yeah, this is a trick that people will sometimes throw at you. They'll give you a few too many variables and make you try and take them out using equations that they give you. So now, because our equation has only v and r, we can go ahead and take the derivative. So then dv dt equals 3 and 1/3 will cancel. So we've got pi r squared dr dt. And we know that dv over dt is equal to 2. And our r is, well, it's going to be 5. So pi times 5 squared dr over dt. So then dr over t is equal to 2 divided by 25 times pi. And that would be meters per second. Make sense? Good. I think that's enough of related rates for now, just because we do have to cover a couple more topics, but I can give you some more related rates practice problems at the end if you want. Okay, let's see. So, if we wanted to, the next topic is going to be finding extrema. Which are maximums and minimums. And to do this, I've actually made a little graphic just to show you what's going on. So give me just a second. Okay, so the whole theory behind finding extrema using calculus is that when the derivative is 0, our tangent line is flat, right? Which is horizontal. And that means we have the chance to have a maximum or a minimum. And the reasoning behind that is, watch what happens in this case when the derivative goes from negative to positive. So you can see our tangent line actually switches from being negative to being positive. And what that means basically is that our slope, it goes from decreasing to increasing. Our function stops decreasing and starts increasing. And you can see that through this tangent line. And because our function stops decreasing and starts increasing, there must be a spot where it's at its lowest point. So there must be a minimum. And that is exactly where our tangent line is horizontal. If we wanted to look at a function that had a maximum instead, for instance, negative x squared, then our tangent line starts out positive, or our derivative starts out positive, our function is increasing, and then it decreases. And the point where it has a maximum is again where our derivative is exactly equal to 0. Our tangent line is horizontal. There are a couple of situations you do need to be careful of though, because not every point where the derivative is 0 means that we have a maximum or a minimum. For instance, if we get the function x cubed, you can see that our derivative starts out being positive. So it goes down, touches 0, but then it remains positive. There's not a point where we have a downward tangent line. So our slope is always positive, or 0. And because our slope is never negative, we can never be decreasing, so we don't have a maximum. And I'll actually go ahead and work out a few problems. But basically, big takeaway from this is that whenever you have a function switch from a negative slope to a positive one, you're going to have a minimum, as you can see right here. And whenever you have a function switch from a positive slope to a negative slope, as you have here, you're going to have a maximum. And if you have a function that does not actually change the sign on the slope, that is going to be neither a maximum nor a minimum. Let's go ahead and do some example problems. We'll start with the function f prime of x is equal to x cubed. Actually, sorry, skipping a bit. F of x is equal to 1 over 4 x to the 4th minus 1/3 x cubed minus 2x squared plus 4x plus 3. Then our first derivative, prime, should be equal to the derivative of 1/4 x to the fourth is just x cubed. Derivative of negative 1/3 x cubed is just negative x squared. Then 4x plus 4. And if we wanted to if we wanted to factor this, all we have to do, we can actually factor by grouping. So for instance, if we chop this function in half, we can see that this is x squared times x minus 1, and this is negative 4 times x minus 1. Since both of these have an x minus 1, it becomes x minus 1 times x squared minus 4, which is x minus 1 times x minus 2 times x plus 2. Since x squared minus 4 is the difference of squares. So that is our first derivative. So in order to find maximums and minimums, we're looking for where that horizontal tangent is 0. Or in other words, our first derivative is equal to 0. And since I went ahead and factored this, it's really easy to tell that our first derivative is equal to 0 at x is equal to negative 2, positive 1, and 2. So now we just need to look at where the derivative changes signs and how the signs change. Like I showed, we need to look for where the derivative switches from negative to positive, or that tangent line switches from being a negative tangent to a positive tangent. That is going to get a min. You can see it goes from negative to positive. If you have positive to negative, that's going to be max, and if we have neither, then it would be neither a minimum nor a maximum. The way I like to see where our function changes, so I like to just draw a little number line and put down the points, negative 2, positive 1, and 2. It doesn't have to be super exact. We just want to make sure we get all of our 0 points on here. And then all I say is, well, what is f prime of x positive or negative for a number that's less than negative 2? So I look at this and I say, well, if I plug x is less than negative 2 into this x minus 1 term is going to be negative, this x minus 2 term is going to be negative, and this x plus 2 term is going to be negative. So that's a negative times a negative times a negative, which gives us negative. Next up, we would need a value that's between negative 2 and positive 1. And I can look at this and say, well, this x minus 1 would be negative, this x minus 2 would be negative, but then this x plus 2 term would end up being positive. And then I keep going through the process from 1 to 2. This x minus 1 term would be positive, this x minus 2 term would be negative. Oops. And then this x plus 2 term would be positive. So positive times a negative times a positive gives a negative. And then lastly, for x is greater than 2, all three of these would give a positive value. And this tells us that we have a decreasing slope and an increasing slope and a decreasing slope and an increasing slope. So you can see at negative 2, we've got a decreasing into an increasing, so we would need a minimum. At x equals to positive 1, we've got an increasing switching to a decreasing, so we would need a max. Sometimes I like to draw these little lines just so I can see this makes a V shape, which is like a minimum, so it'll have a bottom point. This makes a little mountainy shape, so we're going to have a top maximum, and then at x equals 2, we're going to have another minimum. So we can say that our function f of x has minimums at x equals to negative 2 and positive 2, and it has a local maximum at x is equal to positive 1. Make sense? Great. In that case, I'm going to go ahead and give you a couple of practice problems. First up, we're going to start with f of x equals x to the fourth minus 4x cubed. Okay, and then our second one is going to be h prime of x is equal to minus 2 times e to the x. And the second one, it's a little trickier because it's more of a conceptual question, but I think you can get it. I think that 1 is a maximum at x equals to 3. I think it's a maximum, huh? Can you double check that it's a maximum? That is perfectly fine. I'll go ahead and work this one out. So our first derivative is 4x cubed minus 12x squared, and if we factor out a 4x squared, we get that's 4x squared times x minus 3, and that is of course going to be equal to 0 at x is equal to 0 and x is equal to 3. So then if we drew out our number line, we get, we're going to need to put our 0 and our 3 on there. If we look at where, so first off we need to plug in a number that's smaller than 0. In this case, this x minus 3 term would be negative. This 4x squared term would be positive because anything squared is positive. So if you have a positive times a negative is negative. If you plug in something smaller than 3, but bigger than 0, this would still be negative, and this will be positive. So positive times a negative, still a negative, and if we plug in something bigger than 3, all our terms are positive, so we're left with something positive. If we actually drew out a visual representation of the tangent line, we've got negative, negative, positive. And in this case, it's pretty easy to see. Here, this should be a minimum because these two make a valley, so there has to be a lower point because on either side, the function should be bigger. Make sense? Great. And I noticed that you didn't have 0 being a maximum or a minimum. That's great. You can see the derivative doesn't change signs, so it's not going maximum or a minimum. You can see that these two tangent lines don't necessarily line up, and our function is probably something that looks something like this. Where we've got a point where the tangent line is 0, but it just goes from decreasing to 0, then back to decreasing. Now, have you looked at number 2 at all yet? You tried, but you don't know? All right, that's fine. Let's actually think about this. In this case, we're already given the first derivative, so we don't need to take the derivative at all. All we need to do is we need to think about when this derivative here is equal to 0, because that's where all of our critical points are. That's where we can possibly have a maximum. So all we need to do is we need to solve where negative 2e to the x is equal to 0. So what values of x make this true? Are there any? Is negative 2e to the x ever equal to 0? Not quite. E to the 0th is actually equal to 1. So one way to simplify this is we can just divide both sides by negative 2. So we're looking for where e to the x is equal to 0. Do you remember what the graph of e to the x looks like? No? Alright, that's fine. I'll just draw it out for you really quick. The graph of e to the x, it's an exponential function. So it actually starts out like this and then just gets very big like this. So it actually has a horizontal asymptote at x is equal to 0. So it actually never is equal to 0. So this problem was a bit of a trick question because our first derivative is never equal to 0. So that means that regardless of what our function is, we know that it cannot have any maximums or minimums, no local max or min, because it never has any points where we have a horizontal tangent line. There's nowhere that it could possibly have a maximum. Does that make sense at all? All right, great. Now we'll go ahead and move on to our last topic, and that is going to be Rule's theorem and the mean value theorem. That's MVT. I'll start by giving the formal definition. So let's say you have a function f, f of x, and we'll say it is continuous on this interval from this closed interval from a to b. And it is also differentiable on the open interval from a to b. So everything in between a and b, but not necessarily at a and b itself. Then there's a point C in AB so that our first derivative of C is equal to f of b minus f of a divided by b minus a. And basically this is a complicated way of saying that if you have a function that's differentiable, basically you have a function that doesn't do any weird things like jump, have discontinuities, or make sharp turns. You just got a function like this, and you're looking at it on an interval from a up to b. So from here to here, we'll say. Then there's a point on this interval where our derivative, or our tangent line, is equal to this average slope between these 2 points. So between any 2 points a and b, we can draw our average slope, and all the mean value theorem says is that there has to be some point in between these 2 points a and b where a tangent line is parallel to this line between them. So I'll go ahead and do an example really quick. Let's say we have f of x is equal to x to the 2/3 minus 1, and we're on the interval from 1 to 8. We can see that since this is a continuous function, basically it doesn't do any weird things. It's continuous, it's differentiable. We can mostly ignore those two conditions. So we need to start off by saying, well, what's our average slope on this interval? That's just going to be the end point minus the start point over the distance traveled, so 8 minus 1. And of course, 8 to the 2/3 minus 1 is going to be the cube root of 8, which is 2 squared, so 4, then minus 1, which is 3, minus f of 1, so 1 to the 2/3 is just 1, minus 1 is 0, over 8 minus 1 is 7. So our average slope, I'm going to write that MAVG equals 3 over 7. And our mean value theorem says that somewhere there's a point C where f prime of that point C is equal to our average slope. And C should be in this interval from 1 to 8. And it's our job to find out what that C is. So to do that, we need to first find out what our derivative is. That's 2/3 x to the minus 1/3. And then we just have to let that equal to our 3/7, because that is our average slope. And then we would solve for x, which in this case would be our C value. So our mean value theorem says that 2/3 C to the minus 1/3 equals 3 over 7. And we just solve for C, So we multiply both sides by 3/2 to get rid of the 2/3. We get that c to the minus 1/3 is equal to 9/14. And we know that c to the minus 1/3 is 1/c to the 1/3. So then c to the 1/3 is equal to 14/9. So c equals the cube root of 14/9. And we can see that this is bigger than 1 because it's inside the cube root we have a number bigger than 1, but also less than 8. So this is our c value. And then f prime c would be equal to 3/7. Does this make sense? Great. And Rolle's theorem is basically just a specific application of the mean value theorem, where instead of having 2 points A and B, it's just saying that the y value has to be the same, or in other words, our average slope is equal to 0. That's Rolle's theorem. It's just one specific instance of the mean value theorem. But he came up with it before the mean value theorem was around, so that's why it's named after him. So let's go ahead and do a couple of practice problems. We'll start with the conceptual one. Why, that's a terrible why doesn't the mean value theorem apply to the function f of x equals to 2 absolute value of x minus 2 plus 3 on the interval from 1 to 3. This goes back to those conditions that it has to be a couple of things before you can apply the mean value theorem. And our second practice question is going to be function f of x equals x squared minus 4x plus 3 on the interval 1 to 5. All right, go ahead and try those out. 1 does not apply because f prime of c is not in between the interval. It's true that f prime of c isn't in the interval, but can we necessarily find f prime of c for every spot at interval? Oh, right, we've got the absolute value function, so that's going to make a pointy end, right? So because it's pointy, it's not smooth. We've got a sharp turn, and because we've got a sharp turn, it's going to be not differentiable at that point, and that doesn't satisfy the second condition that it has to be differentiable. So that is why we can't apply the mean value theorem. So this is something you'll occasionally see in terms of what's going on. Okay. Let's see. Did you get the second one? Give me a second. My computer is being unhappy with me. Sorry about this. Okay. Unfortunately, my computer appears to have frozen up a bit. So I don't know if you're right because I can't check the chat, but basically the way we would solve this one is first we need to find what f of 1 is, that's 0, and f of 5 is equal to 8. So we would perform f of 5 minus f of 0, so 8 minus 0, which is 8, divided by 5 minus 1, which is 4. So 8 divided by 4 is going to be 2, correct? So in that case, we need to find where our average slope, our slope is equal to 2. So we take the derivative of f prime of f of x. Derivative of x squared minus 4x plus 3 is 2x minus 4. So that is equal to 2 when x is equal to, let's see, we've got 2 equals to 2x minus 4, so 6 equals to 2x. So c should be equal to 3. That's how we solve the mean value theorem. Anyway, I am going to restart my computer since it's frozen up. Alright, sorry about that. But I made it back. Let's see. Now I could hopefully finish going over the second problem. You give me just a moment to get everything. It doesn't seem to want to. Okay, well, let's see. Thank you for coming. Do you have any other questions? Unfortunately cannot answer them right now, but I would be glad to point you towards your tutor. My computer is very not happy with me today. That is very not happy. I cannot move anything. Sorry, I cannot actually see this question.